In the previous video, we explored three methods for detecting outliers: local outlier factor, isolation forest, and one-class SVM. In this video, we'll apply those methods to the Iris dataset, implement outlier detection in code, and visualize the results using PCA. In particular, this example treats one species of the Iris dataset as normal data and another species as outliers, allowing us to compare the performance of the three outlier detection algorithms. You can download the coding file from GitHub and try running it yourself. First, let's take a look at three representative methods for detecting outliers: local outlier factor, isolation forest, and one-class SVM, and understand their basic principles. Local outlier factor detects outliers by looking at the local density around each data point. Normal data points tend to have a similar density to their neighbors, while outliers are found in regions with relatively lower density. Isolation forest detects outliers by repeatedly splitting the data and isolating individual observations. Normal data points are difficult to isolate, whereas outliers are relatively easier to isolate. Finally, one-class SVM transforms normal data into a high-dimensional feature space and learns a decision boundary that encloses the normal data. Points that lie inside the boundary are considered normal, while those outside the boundary, especially toward the origin, are classified as outliers. Then let's implement the three outlier detection algorithms using code. First, we import the necessary libraries: NumPy, Pandas, and min-max scaler for data normalization. We'll also bring in matplotlib for visualization and PCA from scikit-learn for dimensionality reduction. In addition, we import three outlier detection algorithms: local outlier factor, isolation forest, and one-class SVM, along with evaluation metrics such as the confusion matrix to assess their performance. Next, we load the Iris Excel dataset and store it in a variable called df. Using the shape command, we can see that the dataset contains 150 rows and 5 columns. Finally, by using the head command, we can preview the first 5 rows of the dataset. By using the unique command, we can check the species included in the dataset: Setosa, versicolor, and virginica, a total of 3 types. Each species contains 50 samples, so if we select only Setosa and virginica, we'll have 100 data points in total. Among these, we'll label Setosa as 1 representing normal data, and virginica as -1 representing outliers. After this labeling step, you can see that the new label column has been created, where Setosa is marked as 1 and virginica as -1. The input data includes 4 features of the iris flowers, so we'll remove the unnecessary species and label columns and assign the remaining features to X data. Then we'll assign the column containing the normal and outlier labels to Y data. After that, we'll use the min-max scaler to normalize the X data so that all feature values fall within the range of 0 to 1. Next, we define the models. We can organize the 3 models in a dictionary format, where the model name is the key and its corresponding hyperparameters are the value. For local outlier factor, which detects outliers based on the local density of data points, nNeighbors specifies the number of neighboring points to consider. We also set novelty equals true so that the model is trained only on normal data, allowing it to determine whether new data points are normal or outliers. For isolation forest, which detects outliers based on how easily data points can be isolated through recursive splitting, contamination specifies the proportion of the training data assumed to be outliers. For example, contamination equals 0.05 is used to set the threshold so that the top 5% of training samples with the highest anomaly scores are classified as outliers. If this value is too high, normal points may be misclassified as outliers. If it's too low, actual outliers might be missed. Finally, One-Class SVM learns the decision boundary of normal data and classifies points outside this boundary as outliers. We use the RBF kernel, where gamma controls the complexity of the boundary, and nu sets the maximum proportion of training data allowed to be treated as outliers. For instance, nu equals 0.05 allows up to 5% of the training data to be considered outliers when deciding the decision boundary. After defining the models, we train them using only the normal data. During testing, we evaluate the models on the entire dataset, which includes both normal points and outliers. Finally, we store the true labels for each sample to record whether it is normal or an outlier. In this step, we display the prediction results of each model and visualize them using PCA. We compare the performance of the models using metrics such as the confusion matrix, precision, recall, and F1 score. Using PCA, we reduce the four-dimensional data to 2 dimensions for visualization. In the graph, blue points represent normal data, while red points represent outliers. This visualization allows us to intuitively see how well each algorithm separates normal points from outliers. In this example, for isolation forest, we set contamination to 5%. With 50 training samples, 5% gives 2.5. But since the number of outliers must be an integer, the threshold is generally adjusted to classify 3 samples as outliers.